so far at least. I have to admit that that I am currently now one lap behind, but there for a while I was keeping pace. So you don't need to change any pace on my account, over.
Okay, I was just curious because I noticed we don't have quite as many people attending, and I don't want to get too fast where people are feeling like they don't want to attend the live presentations because they're behind.
Well, I get stuff whether I'm behind or not, so from that standpoint, I'm glad that you're going anyway.
Okay. All right, I think we'll go ahead and get started for today then. Today we're going to cover compiler directives. Then we're going to take a look at simulation management. Then we're going to look at test benches. And then we're going to start to look into what's called bus functional models, or BFMs. So let's take a look at compiler directives. I'll get my screen set up here. So compiler directives are not part of the Verilog language per se, okay? But they instruct the compiler to take special action. And the compiler directives remain active across files, and they must be on a line of their own. They can be indented with white spaces, and they all start with a back quote, or I call it a tick. And they do not end with a semicolon. So you've seen this example before of timescale, where we had tick timescale 1 nanosecond / 1 nanosecond. So this is a compiler directive. There's another one called reset all, and that resets the compiler to the default state and cancels the previous directives. So there's a syntax for it. Timescale, you're familiar with that one already. And the tick define, this is a very useful one. This defines an alias or a text macro. So here's the syntax, tick define, symbol name, and then whatever text that you want to put. Here's two examples where we have tick define, base address, and here we have an actual number. But it doesn't have to be a number. It can be anything. It can be, it's just text, okay? So you could actually put a write statement. Now notice this semicolon is not part of this define, but it's actually part of this write statement, okay?
Question?
Yes.
This is Joe again. I just realized that this back tick that you talk about is actually different from what I am trying to use. I always use an apostrophe, and I don't see a back tick on my keyboard. Is that a problem?
Look, yeah, look, do you know where the tilde key is on your keyboard?
Yeah. Oh, yeah,
it
yeah.
should
okay.
be on that one.
Yep, it is. Thank you.
Yeah, I know. It's a little strange at first.
Okay.
Yeah, if you use apostrophe, you'll get a problem. Okay, good. Yeah, that's a good thing to note. Any instance of the tick symbol is substituted with the replacement text before the compilation. So that's why this is just text. It doesn't have to be a number. It can be actual, maybe some Verilog code that you want to put in. So here we've defined a couple things. One of them is this error, where it's this write statement. So here we've actually used it by going tick error, okay? And here you can see what it actually turns into. This tick error turns into this write statement, okay? And then this write statement, notice that it uses tick base address, and so it substitutes this 16 tick hex 00FF for this in the code. So it's a substitution. So many use defined symbols for constants instead of parameters. I don't know if we've talked much about parameters, but we're going to talk about parameters and define today and when you would use one versus the other later on. So here we have a define cycle of 100, and then here in the code, instead of using the actual value right here, 100, we've used the define for it. So you just say tick cycle and then divide by 2. Okay, and if you want to do it using a parameter is actually a numeric value constant. and you substitute it just like this. So these are two ways of doing the same code. For symbolic literals, parameters are better because they're local to the module, whereas the defines symbols are global. Remember that, they're global. And they can be modified on a per instance basis, whereas defined symbols are set when they're compiled. So, and defined symbols are better than parameters when the definition needs to be global, and the definition needs to include an arbitrary Verilog code, not just literals. So here again, here we have word defined as this arbitrary Verilog code that we want. And here we've actually used it that way. So here I've said tick word, which substitutes this literal, this text, basically just substitutes it in here. So here you have ms byte, ls byte, concatenation equals 16 tick hex FFFF. And here we're doing a case statement based on those ls byte, ms byte concatenation. Okay, so you can't do this type of thing with parameters. You can also use tick fdef, tick else, and tick endif. And these can conditionally include or exclude code on the existence or absence of a defined symbol, respectively. And the else clause is optional. The symbol only needs to be defined when it's defined as is irrelevant. Sorry, let me state that again. The symbol needs only to be defined. What it's defined as is irrelevant. Okay, so in other words, if you just say tick define and then some name, you don't have to put any value or any text after it. The if def is just wanting to know if you've defined it at all. So here you said if def some symbol name, and then the else is optional, and then endef. So this part of the code is included if the symbol's defined, not whether it has some value or not, just whether you've even defined it. And then if you did this else, then this here would be included if the symbol's not defined. So let's look at an example. Here I've said define, use BEH, or in this case a behavioral model versus an RTL model. So notice I said 0. Doesn't have to have anything there if I don't want, because all I'm looking for is to see if it's defined here as to whether or not I'm going to do this UART instantiation or whether I'm going to do this UART instantiation. So in this case, because use BEH is defined, it's going to substitute the UART BEH. So it'd be the same as doing this. UART BEH is what gets compiled. Okay. So like I said, the sentence can be defined to nothing, okay? And you can do this also on the command line. You can say plus define and then one or more of these symbol names. So now when I say Verilog here, this is just your particular Verilog compiler, whether it be ModelSim or whoever. So this is just generic here. And here I've said plus define, plus foo, plus bug. So I've made two defines here, foo and bug. So if my code is looking for those to do something based on them being defined, this is how I can do it at the command line. So they're primarily used to control if-def directives, you know, whether you're going to include one code or not another or some other code. And some simulators can define a symbol to a particular text string, okay, but not all of them can. In this case, this is Verilog XL, and they allowed it. Here's another example. Here we have a module called top, and I have various if-defs in here. Here's one here, here's one here, and here's one here. So depending on which of these are defined, it's going to include some optional Verilog code, some initial statements I have here. Okay. So let's say I did a compile and I said plus define on the command line plus signal scan. Well, in this case, when it compiles the code, it'll include this initial statement, $record vars. So maybe for signal scan, you wanted to do that. Maybe for a GTK waveform viewer, you wanted to do a dump vars so that you can create a VCD file that GTK wave could use. So you can include whichever things that you want doing it this way. So at compile time, you can select what type of system that you want in the end. And you can have it set up to do various ones. Okay, the if-def versus the if statement. The if statement can only be used in procedural, and we're talking about an always or initial blocks. And the decision is performed at runtime, and it can only include or exclude sequential statements. The if-def directive can be used anywhere in the source file, and the decision is performed at compile time, and it can include or exclude arbitrary lines. So that's the difference in the two. Tick include. You can include a file, and it compiles it in line. Here's a syntax, tick include, and then a path name. So you could have some local file that you're including. And this .vh, you can put anything you want here. This is just, some people use that. You might have something like .inc or whatever extension you want is fine. It doesn't matter. Here's one where the path is a little more elaborate, where we've backed up a directory and gotten something from a different directory. One thing to remember is that included file names are relative to the current working directory where Verilog is run. Included file names are not relative to the file containing the include directive. So let's say that we had changed our working directory to right here, and I had a file called model.v, and it said include common.vh. Well, in my directory structure on the current working directory, I have a file called common.vh, and in a subdirectory source, I have model.v and common.vh. So when I go to compile, I say vsim source model.v. Okay, because of what I told you here, it's going to use this common.vh and not this one. So that's something just to keep in mind. Directories to search for included files can be specified on the command line, and you use the plus incdir with one or more plus path names. So here's an example. Verilog, your plus include directories, plus whatever other source directories you might want to add. That's an example. So what you're going to do in Lab 7.1 is you're going to learn to recognize common mistakes with compiler directives. Then you'll learn the difference between the if statement and the if-def directive. And you'll learn how to create reconfigurable models. So that should be a fairly simple, straightforward lab, I think. Talk a little bit about simulation management now. Required source files can be specified explicitly on the command line, and path names can be relative or absolute, and the order is not significant. So here's syntax, and here is an example or two where we've included each file on the command line, or you could say star.v, which would the shell, your OS shell would include all of the .v files. Also, required source files can be specified using a file containing commands that will parse through that file. And the syntax is right here, -f and then file name. Okay, some people call these a manifest file. So here in this example, I've said to compile using that particular file, -f and then the file. And this name is arbitrary again. Okay, you're not stuck to any particular extension or anything. So in this file, I've said now to include all of those .v files in what I'll call this the manifest file. So you can do it that way too. You can also mix and match. You can put a file name, like in this case, maybe this is my top level Verilog module. along with a manifest file for it to parse through. So here's an example of that. You can use manifest files to hide model configuration, and you only need to know the manifest file, not the detailed composition of the model. So here's an example where I've said, in this particular case, I want to compile this, simulate a model that's a behavioral model of my implementation. Whereas in this one, I want to simulate using an RTL model. So I've created two different manifest files with different things in them depending on whether I want to do my behavioral model or my RTL model. And this is an example. Manifest files can contain any command line options, and the manifest files can be hierarchical. Here's another example where I said compile with this top.v and again with this manifest file. And here's an example, files plus more information. Okay, I've called this other manifest file. Okay. Or the details of a particular configuration can be left to the user. Here's just another example of doing this. Okay, gate level models use hundreds of different modules. Okay, and they may not want to you may not want to maintain detailed manifest files. Frequent changes after each synthesis is run. Verilog can automatically pick source file that things contain missing modules, and we can scan directories known as libraries. So let's take a look at how you can do this. So library directories are specified using the -y option. Here's the syntax, -y and then a path name. You can also specify a library file name suffix using the +lib.ext option. You want to probably look at your particular compiler, go into its documentation and see all the different things. So some of these may vary just a little bit, and look to see exactly how yours will handle it. Here's another example where we have a file called gates.v, and in here it's using a instantiation called act2. Okay, and here I said to compile. Oh, wait a minute. I think I missed something here. Yeah, sorry, this is a new presentation. I kind of mixed one slide with another slide, kind of got messed up a little bit. But basically, using the -y, you can specify a library that will have all of these different modules in it, or all of these .v's in it, and it'll find the particular one that's missing or needed. And so here's a command line option here, -y/tools, and this is a directory. And we've declared this lib.ext, and it'll look throughout that to find the missing one. I'm sorry, this slide didn't get done correctly. So some vendors prefer to put all the modules in a single file, such as in this case here. This one probably had all the modules within that one file. And you can use the -v option to treat the file as a library file. And then only the required modules will be imported into the simulation to pull in just the ones that you want. So you can put -v and then the actual file name. This is a new lecture. I did this afternoon, so I thought I had it cleaned up, but it's not quite. But anyway, here it is again. Here we compiled the gates.v, and here we've called this particular add to module. And in this particular path, there's a file called verilog.v, or it could be any other .v file. This I could say all my verilog.v. And in there are all these different modules for all these different things, and it'll extract just the one that's needed, in this case, the AD2. And here's the command line up to do that. Okay, in this case, it doesn't know.
Hey, Kirk, I have a question. This is
Yes.
Mike Krieger.
Hi.
So the -y can only be, do you have to have all the modules the same file name to be able to use that?
Let me check on that. So you don't know if all the modules. Say that
Or does
again.
it like, or does it like parse through each of the? Does it include all the code and then figure out what it needs?
It should
You
parse
have to
through
have the
that
same-
directory. It should parse through
Oh,
that
okay.
directory and find them. Or it should look, not parse, but I mean look through that directory. So in this one, this was just a directory, and all of these .v files were in there. Okay, so -y tools, there's the directory. So it'll look at all the .v's.
Question?
Okay.
Then what's the difference between the -v and the y?
The V, all the modules are within one file.
Oh, okay.
I think I messed that up for you. Sorry about that.
That's okay.
So here's the -v again. Okay, we've told it this particular file. Maybe I shouldn't have said Verilog here. Maybe I should have said all my modules.v. Okay, and this is the actual file that I'm talking about right here. This Verilog.v is this one, and it contains all of the modules in it. Sorry about that. The manifest file can contain any command line option. The manifest file for gate level models should include any necessary -y or v options. So here's just an example of using the different options within the file, and you can look at this and play with some of that. Whether you use -f to parse another file, and this one uses a -v to go through a specific file looking for modules, or whether it goes through a directory looking for those particular modules. So in Lab 7.2, you're going to learn how to specify simulation files using the -y and the -v option, and learn how to manage simulation configurations using the manifest files and the -f option. So we're going to go back to what good is Verilog. So far, we've learned that we can describe concurrent systems and structural systems, but we still need to be able to test that a model is correct. So that's where test benches come in. So how can we be sure that a model is going to be correct? Well, we do that through simulation. So we need to be able to provide a stimulus, and we need to be able to observe the response of the system. And so we create what's known as a test bench, which is an environment used to test a model. So in real life, maybe you have a signal generator and some test equipment, an oscilloscope to look at signals coming out, and you would physically hook up to your circuit. Okay, so if we were to model that in Verilog, we would have something where we have maybe one or more signal generators going into our Verilog model, and then for the outputs, we need something to observe the signals coming out. So the question is how do we describe this type of stuff in Verilog so that we can see some meaningful output and see if our model is doing what we want it to? Okay, these of course would be called our ports that we've talked about in the past. The connections, the in and out. Okay, so we use Verilog to actually describe these type of things right here. So we would create Verilog models of our environment along with our Verilog model of what we're trying to create. So let's say, in a simple case, we just want to test an inverter. And so for an inverter, you feed it a stimulus with like a 0 and a 1 and then a 0 over time. Okay? So you're going to observe the output of that inverter over time, and input values and output values. You're only going to see how things change. Okay, and you're going to observe how it reacts at time 0 versus how it reacts at some other point in time after an input or an output has changed. So let's say that we have an inverter module, just a simple module. So it's got a single input, single output. Okay, so let's make another module called test bench. And in that test bench, we're going to instantiate that inverter. Okay, so if we go back a couple of slides here, this is our inverter, and then we're going to create a test bench outside of that. Okay, so far we've just done this. Now, what else do we need? Well, let's create a stimulus. So we'll create an initial block, and we'll say that, okay, so at time 0, we're going to set the input to 0. Then we're going to delay 100 time units, whether they be nanoseconds, picoseconds, or whatever you use with the tick timescale directive. So we delay 100 time units, set the input to 1, delay another 100 time units, set the input to 0, and delay another 100 time units. Okay, so maybe we add that in. Now maybe we add some more code like this. We say always add I or O. Anytime that the input or the output changes, we're going to write out some information. So in this case, we're going to print out this %0D, so it's going to print out the current simulation time. We're going to print out the value of the input, and we're going to print out the value of the output at that current simulation time, anytime I or O changes. So somebody comes along and they ask you, well, what is the inverter's propagation delay? So we need to be able to produce an output that's meaningful with respect to the questions that were asked or what we're supposed to be testing. So we're going to have Verilog do some of that for us. So here, let's modify our initial block that we had a little bit. And we're going to declare a time register called last I. And then what I'm going to do is then after I've set I to 0, I want to record that time. Okay? Every time I change I, I'm recording that temporarily in this time register. Okay? Then I've said down here, always at output. So anytime the output changes, I'm telling it the propagation delay equals then the value. Well, the value will be whatever the current simulation time is minus the last that we recorded. So that way we can compute an input to output delay. Okay, so this might be one way. Maybe you want to modify it a little bit. So you want to be able to observe rise and fall delays that might not be identical. And so here we've modified that always block now. And we said that, oh, okay, if the output is high, then I'm going to write rise. Otherwise, I'm going to write fall, and then I'll write delay equals, like we did last time. So that way we can see what edge it is and what the delay is. So this is just the beginnings of how you can start to do simulation. So in the lab, I want you to learn to write a behavioral test bench and how to produce some sort of meaningful results. And we're going to get more into bus functional models in our next lecture, but I'm going to touch on them now. And as we go along, you're going to get deeper into how to simulate your code and how to feed stimulus and get meaningful results. So let's touch on bus functional models today. And there you use tasks to abstract repeated operations. Now, we talked about tasks in the past, if you remember, and we'll go through some examples today of how to do those. Abstract detailed operation, okay. You're going to abstract detailed operations into high-level commands. So let's take an example of a scannable D flip-flop. So this flip-flop basically has two inputs, the regular D input and the scan mode input. Okay, and that's the SI signal. And the SM is just whether it's in scan mode or not. So if it's 0, it's going to use the D input. If it's a 1, it's going to use the scan input. And then this is our clock symbol. And then we have our Q and our Q bar output. So we could start off writing explicit controls to do it. So let's just see how we might do it that way. So first thing we might want to do is reset the flip-flop. So we'd set the reset line. Let's go back here. There's the reset R. Okay, so we'd set that high, set the D input high, and the scan mode input high. Then we wait for the positive edge of the clock. And then here I've said delay, and this is, I'm delaying somewhere I've defined this, that our clock to Q, because remember when you're clocking a flip-flop, there's a propagation delay from the time that you clock it, the clock edge going high, to the actual output being there. So I want to wait until I know that the output is going to be there based upon the input. So here I've just said delay this clock to Q output time. And then I test to see is Q going to be defined as 0 and Q bar as 1, because we're doing a reset. Okay, so it shouldn't follow this D at all or this SI. The Q should go to 0, not the D. So if this isn't true, then I'm going to write out some error. And then I continue on and I say, okay, if that's okay, then let's test the data in. So here I've set the reset to 0, so this would be normal operation for the flip-flop. I've set the data input pin high. I set the scan mode input low, because I'm going to use it in regular mode, not scan mode right now. Here's scan mode set to 0, which says use the D. So I'm setting it the opposite of D, so that after it clocks, I want to make sure that I get what's on the D and not on the SI. So here I clock, and then I delay to make sure my Q is going to be valid by the time I check it. And here I'm checking to see that Q is equal to 1, the same as my D input. Okay? If it's not, then we've got a problem and we write something out. So here we've done explicit Verilog code to do that. So in this particular test, there's 3 things we might want to do. We might want to do not only test the reset, and test the load data. We also want to test the scan data. So what we can do is create a task for each of these procedures. Okay, and we can use arguments to pass specific information to complete the procedure. And never mind that last statement. Okay, so let's start off with our reset tasks. What do we want to do? Well, we're going to assert reset. We're going to set all the data inputs to 1. We're going to wait for the rising edge of the clock, and then we're going to wait for the clock to Q delay, and then we're going to check the Q and QB and make sure that they were reset. So that's our reset task that we want to do. So let's write this reset task. Here I've just said, okay, that clock to Q is 1. It can be whatever it needs to be for your particular test. But here I've defined my task, reset. And in here I've set the reset high, so it's in reset mode. I've set both the D and the scan mode input to 1. We've waited for the clock, waited for the clock to Q output delay, and then we've done our test. And that's all we're going to do for that task. Okay, now we're going to look at creating the load data task. So in the load data, we're going to need to deassert the reset. We don't want that active. And we're going to deassert our scan mode. And we're going to set the data input. And we're going to set the scan input to the opposite of data to make sure we're getting data, not scan input. And then again, we're going to wait for the rising edge of the clock and the clock to Q delay. And we're going to check our Q and Q bar again to make sure they're set appropriately. Okay, and the operating parameters for this is some sort of data input value for the task. So let's look how we might write that. Again, there's our parameter for our clock to Q. It can be whatever you need it to be. We've set our reset to 0 in this task. Here we've got our data in. Okay, so you can feed it whatever value you need to feed it for the test. Here we've set our reset to 0. We've taken it. We've made sure it's not in scan mode. We've set D to be whatever the DEN is. And we've set the scan input to be the opposite. Then we wait for our clock edge, wait for our clock to Q to make sure the Q is going to be output correctly. And then we test it. And so we want to make sure that the Q, in this case, for the normal operating mode, Q should be equal to the data in. Okay, and Q bar should be the opposite of that. So if it's not, then we're going to write out some error. So then your test becomes a sequence of high-level operations, which are easier to understand and maintain. So now we can just call those tasks. Reset, data in, feed it the value we want, data in again, feed it the value we want, etc. Okay.
Comment?
Yes.
In this example, then actually, if everything is working, you get no kind of output at all, right? Other than,
yeah.
I mean, you don't see any output if you were to run this.
Yeah, I've just kind of given you a brief. I mean, you can modify it and add a lot more to it. I mean, you could have the simulation stop as soon as it gets an error if you wanted to.
Okay.
Which is typical. You would just put in like a $ stop, and just have the simulation abort right there so that the last message you got was your error message. And then if everything was okay, if you actually made it through here and none of those stops got executed, you could maybe put a write statement in here and say, okay, simulation worked fine.
Yeah, okay, good.
Okay.
I mean, that should have been obvious, I guess, but all right,
No,
thanks.
no, that's fine. Yeah. Yeah, these are really useful, tasks are really useful for simulation purposes.
Mm-hmm.
So tasks that abstract detailed operations without interpreting the transmitted data are called bus functional models, or BFMs, people call them. Okay, so you could create one to say to return data like from a read of something. Okay, and they can be simple like we just did with the input on the flip-flop or the inverter, or they can become very complicated where you're performing multi-byte I/O reads on a PCI bus or something like that. Maybe I can show you some of these here. So we'll have a little time left over now. So in Lab 7.4, I want you to learn to write simple bus functional models and use a bus functional model to test a device. So I want you to start getting used to doing that. That's all of the lecture. Now what I can do is actually show you a little bit of this. In our next lecture, I'm going to go into more detail how you can write more complex bus functional models. And I think what I'll do right now is, if I can get my computer working here. Let's see, what ModelSim. Maybe I can show you an example. Everybody see my screen okay now?
Yep.
Okay. This is an ongoing simulation file that I have, or stimulus test bench file that I have, that I'm using to test my new Aussie Janus Verilog code. And I'll show you. Here's an example of a test bench. And of course, I've got an initial statement in here. And it's got a bunch of things that I initialized, certain values, of course. And you'll see, I'll print, sometimes during the simulation, I'll have it print out things, like a display, and I'll have it do a stop, like I was telling you. Okay. And then, okay, here we go. Here's an example of a task. I call it write USB, and I write this value. Okay, so if we go down further in the code, we should see that write USB here. Let's see, where did I put it? I'll search for it if I can see it real quick. Here it is. Okay. So in this particular case, here's the task with my input 16-bit value, and I, look for certain things, wait for some clocks to happen, and I actually put out a value. And so this is just a little simple task. And so that's another example of how you use them. I have other ones in here. There's a read USB right there. These are very useful for stimulus. And again, here's the actual module that I'm testing. This is one called AussieJanus, AussieJanus.v, and these are all the different IOs that go to it. So all of these signals here, I'm either watching them or else I'm driving them with information to see the correct outputs, so I can observe whether things are happening correctly. Oh, this is a new little module I created yesterday called One Wire. So this is kind of, I was testing it. Okay, does anybody have any questions?
I do.
Okay.
This is Joe again. I noticed in your code here you've got a lot of sequential at, pause, edge, clock kind of statements, one right after another. So are you, the number of those that you have in sequence are, I mean, you already have figured out how many clock edges should occur before the final thing ends here? Is that,
yeah, I've just defined that I wanted it to take a certain amount of clocks for this particular function.
okay.
That's just something I decided, and this is just a stimulus. Now, again,
Yeah.
this is a test bench. This is not something you would synthesize. This is purely behavioral code for stimulus.
I guess the question I'm trying to, or the answer, what I'm trying to understand here is if you took out one of those at, pause, edge, if, clock statements, would then your little behavioral model here fail on you or not?
Oh, yeah, very likely, yes.
Okay, all right, that's what I wanted to know.
Yes, it's just I've created something that I know takes a certain number of clocks.
Yeah.
Okay. Yeah.
Very good.
You could do the same thing if you wanted to just put in some absolute delay value. You know, it took some certain amount of time. You could do it that way. There's various ways that you can do it.
Okay.
Okay. But maybe in this case, maybe I use this because I know that, oh, okay, maybe there's so many flip-flop delays or something, you know, or I just want to make sure I took a certain amount of time.
Gotcha.
Let's see if there's any other examples. Okay, we can look at this one. So in this case, I'm going to generate some data that goes to one of the TLV 320 parts. And here's my initial statement right here. And I said, okay, delay this particular amount of time. I want to make sure I get past a certain point of other things that I'm doing in the simulation before I start feeding this data in. Okay, so I said delay this amount of time, then I look for another particular signal. I wait for another reset signal that I'm looking for. And then I get to the real heart of what I want to send. I want to feed this stimulus of data into the part. So here I've said, okay, I'm going to do this 64 times. I'm going to send this particular data. Now, on the current version of the Aussie and Mercury and stuff, we have a clock pair called CB clock and CLR clock. I don't know if have any of you looked at any of the current code? You know what I'm talking about? These are a couple of signals, CB clock and CLR clock, that are on the Atlas bus. If you look on the schematics, you'll see them on Atlas pins C8 and C9. Okay. So in this case, I said, okay, on the negative edge of this CLR clock, I'm going to send some data, okay, and this happens to be some serial type data that actually gets sent out. So I'm going to call this task TLV data with the value that I'm using for my loop counter here, my for loop, okay, and I'm going to set a couple of signals to unknown, and then after that's done, I wait for the positive edge of the CLR clock, and I actually send the same data again. Okay, so now this task, TLV underscore data, is right down here. Okay, and it takes a 16-bit input, and then I wait for before I send it out, I say wait for the positive edge of the CB clock, and then I wait for the negative edge of the CB clock, and then I start generating this serial data going out with this loop here that goes for 16 times. Okay, and which data bit of the 16 I put out is dependent upon this T count. Okay, so I feed that on the CD out and the CD out P, a couple other signals on the Atlas bus. Okay, and I do that at every neg edge of CB clock. It changes. So if we were to, let's see if I can show you an example here, just a minute. So here, you can, in this particular example, I've showed you that I'm calling, here I have this initial block for this, I'm calling these tasks within it. That's another way you can use it, tasks. Let me see if I can find a file so I can explain these C clock and CLR clock. Does anybody know what the CB clock and CLR clock are? Well, let me see if I can find here. Okay, I made a little diagram here in the code. You can look at it. Just a moment. Okay, here's what the CLR clock looks like in the version that I'm playing with here. Basically, it's 256 clock M clocks it's created, so it goes low and then high. And what happens is that each edge, serial data gets put out. So, and then when it finishes, it waits for the next edge, and a different set of serial data gets put out. One for the left channel, one for the right channel. And CB clock, with respect to the CLR clock, is like this. CLR clock goes low on the negative edge of CB clock. So in my code, once I see the negative edge of the CLR clock, let's go back to that. Right there, negative edge of the CLR clock, then I want to put out this data. And the data gets put out according to, well, what edge of the CB clock? And here's the relationship if we go back. Okay, you can see that when CLR clock goes low, the data needs to go out on this next low-going clock edge. Okay, now depending on whether this happens to come just a little before or a little after, I put in my code, well, the next thing to do is wait for the pause edge of the clock, which will put me here. Then I wait for the neg edge of the clock, so I know that I'm here. Because if this CLR clock, just due to delays, was a little bit before the falling edge of CB clock, and I said, okay, when CB clock goes low, wait for the negative edge of CB clock, wouldn't do it. It'd fail. But in the case where it comes a little slightly after, and I said, wait for the next edge of the CB clock, well, that would put me here. So just to make sure, I said, okay, wait till I see the positive edge of the clock, and then go to the neg edge of the clock. That's what this is about right here. Okay, that way I'm not dependent upon any delay that might be right there. Okay, and then I put out the data, and this is the data coming in at 16 bits. And so I say 15 minus T count. So when it starts off, it'll be bit 15. Next loop, it'll be bit 14. And that's what we want for the data to look like here. Bit 15, bit 14, so on. Does that make sense?
That's slick. As a matter of fact, this kind of explanation that you're doing for us here, I think is probably more important than the more formalized slides are, at least from my perspective. That's great.
It's easier for me to explain it too.
Good. I appreciate it.
Okay, let's see if there's anything else that might be fun. Okay, that was for the TLV data. For the TLV 320, I was doing stuff. And then I have a similar thing where I'm doing it for the AK5394. And in this case, a very similar type thing, different clock, but neg edge, I'm going to send out some data. Then at the pos edge, I'm going to send out some more data. So this is where the test benches are really useful for testing your actual, code that you're going to synthesize. And in my case, this is the module that's actually going to get synthesized. This is AussieJanice.v. And that particular module, which is here, it actually consists of other modules and stuff. In fact, if you look over here in my Verilog thing, you'll see that there's quite a few other modules, some of which are not used by the actual synthesized hardware. I actually have some modules that are used just for simulation purposes too, stimulus. But very useful. And the nice thing is that you can look at some of this stuff. Let's see if I don't know if this. Oh no, this simulation wasn't. This was for something else. I wrote a new little module, actually two modules, and it looks like we're going to actually use these in the code coming up. I call it one wire. So it uses one wire to actually communicate data. So it's got a built-in clock, so to speak. And I don't know if we have time, but if you're interested, we could kind of go through it. It's not a very big module, and you could see how it works. This right here is the actual simulation of it. So here I built my transmitter that sends out data, and this transmitter gets included in the Aussie FPGA, and then this receiver right here, I wanted to simulate it. It's going to get put in the Mercury FPGA. I just tested it this morning and it worked, so I was happy. In this sense, we have a bunch of data that gets sent from the Aussie FPGA to like Mercury and Penny and Janus and the different ones, and it's called command and control. I don't know if you've heard of that yet. Anyway, this data is just, a lot of general information that gets broadcast basically from Aussie to the other boards so that they know like what speed we're running at or which clocks to use, all that kind of information. And so this was a method that I used to do that. And so I just made something up the other day. Anybody interested? Maybe just spend a little time going through this?
I would.
Okay. It just gives you an idea. So what I did is I just came up with a new function. I created it because Phil mentioned, well, maybe we could cut down on the number of data, the number of signal lines we're running on the backplane if we did a one-wire type transmission. So I looked at some of the ones out there, and there's a whole lot of protocol to some of them. And I thought, well, I'm just going to make something simpler. So I thought, well, here's what I'm going to do. This is my transmitter module, and these are just comments I put here at the beginning of it. And the goal is I want to transfer data across just a single wire between FPGAs. So my format is going to be, well, initially when you turn the boards on, they may need to do some stuff to get themselves initialized and ready. So I thought, well, before I transmit anything from Aussie to the other boards, I'm going to wait some delay time. So and it's just a single wire, and Aussie's the one transmitting the data out. It's called D out. So I'm going to wait some delay time. Then I want to be able to send some synchronization so that the other board can figure out the speed at which I'm sending the data, because that's one of the purpose for the receiver is it figures out how fast these bits are. So I'm going to send what I call sync bits. So a logic 0 sync bit looks like this. 1/4 of the time, it's a high. It goes high. And then for the rest of the 3/4 of the time, it'll be low if it's a logic 0. If it's a logic 1, it'll be high the first quarter, then high for the next 2 quarters, and then low the last one. So the unique characteristic here is this time TV. I will always have a rising edge on the sync bit every TV time period, no matter whether I'm transmitting a logic 0 or a logic 1. Okay. Now, one of the keys to this is this data is not that fast. I may be sending blocks of data maybe 1,000 times a second, so it's not very fast data compared to my clocks that are in Aussie, like the 48 megahertz clock that's in Aussie, or the 122 megahertz clock that's in Mercury. So one of the keys for this to work is the sampling clock that we're going to use to grab the data needs to be a lot faster. Okay, and I said at least 8 times faster, which that's no problem. As it turns out, what I'm doing right now, each one of these TV time periods is probably 300 clocks. Okay, so my format is, okay, I delay some time after reset. I send 5 logic zeros for sync bits, and then I send a low on the signal for greater than 2 of these time periods. Okay. Now, and then after I send that low, I send my actual data bits, and the data bits will either be logic 0 or logic 1. And those are sent out for, let's go down here. I tell it how many. Notice this is how you can use parameters too. So I've created this module. It has a reset input, a clock input, the transmit data that I want to send, and then the actual serial single wire going out called D-out. I've created a parameter. I called it clock frequency, and that's the frequency of the clock that I'm going to be using. Okay, my default, if this is put in Aussie, it's 48 megahertz. So I just put that here. But the nice thing about parameters, remember, is when you instantiate them, let's go back to sim.v, is you can override parameters. Okay, here I've instantiated the transmitter in this simulation, and I said, okay, override some parameters here with some different values. So like in this case, data bit 16. For this test, I just want to transmit 16 data bits. But in the code here, my default, whoops, wrong module. My default, I said 64 data bits. In the actual code for the real McCoy here, it's 59 data bits that we're sending. But it doesn't matter. I can override those parameters at compile time to create just the number of data bits that I want. So I write my code. It's called you call these a parameterized module, so that you can actually change them at compile time. They can serve different purposes. You can compile it one way for simulation, but you can compile it a different way for that real thing. And that way you can test it with several different configurations real easy. So here I've said my default sync bits are 5 of those, 64 data bits. And my frame frequency, which is not real critical, I say I want to send a whole frame of data, which would be the in this case 64 data bits. I want to do that 1,000 times a second, and then it'll actually do the sync bits with the low once every second. So that just resyncs, and I'll explain more what these sync bits are actually for.
Question? Question?
Yes, go ahead.
You said the sync bits would be sent once a second. Where did you specify that?
Oh, I have it. It's just down in my code later. Like I call the data bits, so they're going to go out 64 data bits, and then I do that 1,000 times, and that's my actual frame. Let's see if I called right up here. Well, maybe my comment's not up to date, but basically the way I have it working is I'll do 1,000 sets of data bits, and then I'll do the sync bits and the low.
But if you add up all those time delays, is that 1 second?
It doesn't. It's not critical. It's just it needs to be approximate here. I could make it more precise if I wanted to, but it doesn't have to.
Okay.
And the sync bits are merely just for helping the receiver know how fast the data is coming. And I'll show you how that actually works. In fact, maybe we should just go through it now. So on the receiver side, if you were to get one of these sync bits, either a logic 0 or high, you can detect where the signal goes high. Okay? And you can count, based upon your clock that you're using, how many clocks it takes between rising edges. Okay? So I could count, I could set a counter starting to count on this positive edge, and I'll show you how to do that. Anyway, you can start counting on this positive edge, you count until you get to this edge, and you record that value. Okay, it's so many clocks. Let's say 300, it counts. And then it does it for the next one. Say that one's 301, and another 300, and then another 300. And then you could, at the end of this, if you get this long stretch, you can say, oh, I got sync bits. So I'm going to take my average of those 4, and that's going to be the amount of time between rising edges that I'm going to use for collecting data. Okay, so let's say it turned out to be 300, your average. So now when the real data starts, after this right here, you come along, you get this rising edge. Doesn't matter whether it's a logic 0 or a logic 1, you always get a rising edge. So many, this time period, TB apart. So I can say, oh, okay, I know for the first quarter cycle of that, 300 divided by 4, it's going to be high. I don't want to do anything there. I'm going to wait. I'm going to sample out in the middle of this. So at time 150, I can sample, and I can see whether I've got a logic 1 or a logic 0 on the receiver side. You could do it different ways. That's just the way I chose to do it.
Okay, that's slick.
So anyway, I've created all these different parameters, and then notice I created another parameter here, and I said the number of delay clocks is going to be this clock frequency times this delay time, which is in milliseconds, divided by 1,000. Okay, so since my logic here is running on the 48 megahertz clock, this calculation will give me the number of clocks that I need before I start sending out sync bits. So it's a very useful way to use your parameters. Now, if in a module I override and I change my clock frequency to 122 megahertz, then it'll make the correct calculation in order to get the correct amount of delay time. And it'll do that at compile time. So this way your module can be used in different ways. It's not hard-coded, so to speak. Then I have, there's some other stuff here. I have Q1. Man, that to me just represented this first quarter period, Q1, from here to here. Okay, and I can calculate that by taking the frequency, dividing it by the frame frequency, the number of data bits, and then divide by 4. So that'll give me basically what I want to use. I'm not real concerned that it's 100% accurate because the receiver doesn't care. It'll calculate, it'll figure it out. But this is just an approximate, the speed at which I want things to run. And it's fairly close, you know. Then here I have another one I've said that's 3 times Q1, so that's for the first 3 quarters, like to here, because if I'm going to make a logic 1, I need to know how far out to go from the rising edge to make the this go low. And then this low time, I said that's equal to 4 times Q1, 2, 3, 4. Q1, 2, 3, 4 is just 4 times Q1. In other words, it's this period. Q1, 2, 3, 4. And I said that I want this to be low greater than 2 bits worth of time. So I just said, okay, 4 in this case. And then the receiver actually, I think, looks for 3 or something like that. Just, in other words, I wanted it this time to be at least more than 2 or 3 of these clock periods so that we know we got a synchronization thing. Let's see. Well, let me explain this too. You might be interested in this. First of all, these local params, I don't know if I've talked about those. They're like parameters, except that they can't be overridden externally. So externally right now, all of these parameters could be overridden with other values. But I said local param for these because I don't want them to be overridden, because these are calculations based upon these parameters up here, and I don't want anybody overriding them and messing up my code. So that's why they're local params. Now, here's I bet you could use parameters here too if you wanted to. Here's a function. I call it clog base 2. Okay? Basically, I feed it a value. Now, in the case of 64, this would be 63. So if I create a register and I want to be able to hold a value from 0 to 63, which is 64 minus 1, how many bits do I need to do that? 6 bits? Well, that's what this function does. It calculates, well, how many bits do I need to have to contain this value? Okay, so that function is just down here at the bottom. Basically, it takes that max value, 63 in this case, and it goes through a loop, and it keeps shifting the data left one bit at a time until the value of the shifted data becomes 0. Okay, and at that point, it's calculated how many bits are needed to hold a value that big. And then, in the case of this x, I just called it xs. Right here, I've said, so if I feed it a value of 63, it's going to come up with, what is that, 6 bits? Okay? So if it takes 6 bits to hold the value of 63, then I'm going to create a register down here called data count. Goes from 0 to xs minus 1, 0 to 5 in this case, okay, which is 6 bits. So now I can define my register width to the minimum that's required for this module based upon the parameters. Looks a little strange, but it's real handy. That way you don't just feed it an excess of bits that never get used and a bunch of flip-flops that never get used. So here I've just defined just the number that I need. Does that make sense?
Yeah, that's slick.
So I tend to do things like that. And then here's another local parameter. I've defined a bunch of values. Now you could put these on a single line at a time, but this is another format that's fine to use. You just put a comma at the end, and then you put your next one like this, and then the very last one you put the semicolon. So you can do that with parameters. And then I have an always block, and this particular code is going to be running on the positive edge of the clock. And in this case, it's the IF clock, which is 48 megahertz. And then there's a bunch of code in here. Now, all of this code right in here in this always block, this is all going to get, because of the way I've written it for RTL, it's all going to get turned into flip-flops. And then I have another always block, which happens to be state machine. And I've said always at star. So in other words, any of these signals in here, when any of them change, it comes through and it redoes this again. So on you could sit here and you could put parentheses and a list of all your signal names, but I don't want to do that. So this at star notation is much simpler. And that just says any of these signals in here that change, come back through and recalculate this. And in this particular block happens to be my state machine, and this is synthesizable RTL code the way I've written it. And all this code turns into is combinational logic, ands and or gates. Okay? And we can talk more about how it does that, but and how to write state machines. We'll get into that sometime, because that's where the power comes in for writing your code, is writing your state machines and be able to write how to write flip-flops. everything you need. Just a minute here. Let's see. Okay, well, let's just start right here. How are we doing on time, Michael? You need to go?
Yeah, I got to go in about a couple minutes, but
Okay. All right, I'll just mention
gotta
one more
go.
thing here, and then we'll wrap it up for today. Maybe we can talk about this some more in another lecture here, but here I've said that, remember I had at the very beginning, I want this delay time. Well, part of my code for that is right here, where I have this delay count. So in a certain state of my state machine, if it's not equal to a certain state, then I clear this delay count. Otherwise, if the delay count is not equal to that num delay clocks that I calculated up here, right here. Remember I calculated how many clocks at 48 megahertz it's going to take. If it hasn't counted up to that value, then I keep increasing my count. Okay? So this delay count now is several flip-flops. In fact, it's this many flip-flops. DS. Well, what is DS? DS is, okay, I had the number of delay clocks, so let's say that turned out to be 2,000. Okay, well, how many bits does it take to contain 2,000? How many bits do I need in order to hold a value of 2,000? Well, that's what this function again does, and that's what I've declared. It's that big right there. So it takes that, however many bits that turns out to be for whatever that calculation is. I don't have to worry about it. So anyway, it'll sit there and keep counting up until it gets to that value, and then later on in my code, I'll show you how I use delay count. But I guess we better wrap it up for today. Sorry, I just kind of get into this stuff, and maybe you'll get something out of it.
Good stuff. It's good stuff.
Sure is.
This is, as Joe said, you know, it's very useful. You can really see applications and see how to do these things.
Yeah, the real power of Verilog is not just for synthesizing your code, but being able to simulate it.
Yeah.
Okay, any quick questions?
Okay, thanks everyone. You know, for next time, if you want to, you know, go longer, we can start a little earlier. I just can't go too much past 5, but you know, if you know, we can always figure out another thing to do. You know, if you'd like to. But do you want to try to start a little earlier next? Maybe a half hour earlier. I don't know. It's kind of up to everyone who's involved.
Yeah, if they want to, I could just start where I'm leaving off today, and we could talk about this some more before the lecture. If anybody's interested.
That'd be good.
So you could just
so maybe next one we'll just.
Yeah, we could talk about this more, and then I can finish talking about this, and then we can look at my receiver module and see how that works.
Yeah, great. Okay, well, thanks everyone. I'll send out an email stating that if you want to do a little bit more of the code walkthrough, we'll start at 3:30. So thanks everyone. Good night, and I'll post this on the website soon. Bye.
Okay.
All right. Thanks.
All right. Good night.